This lesson is on simplifying radicals, so we're going to look at a way to take the square root, third root, fourth root of a really large number and kind of break it down so it's easier to deal with. So the first method we're going to go over is prime factorization. And so before we do that, I'm going to explain what a prime factorization is. So a prime factorization is when we factor a number using only its prime factors to begin with. So with 27, what I can do is I'm going to pull out two factors of 27, one of which has to be a prime number. So I'm going to pull out a 3 because that's prime, and 3 times 9 equals 27. Now, I'm not done yet because not all of my branches are prime. So I can't break down 3 because that's prime, but I can break down 9, which would be 3 times 3. And now I'm left with all prime numbers. So the prime factorization of 27 would be 3 times 3 times 3. Now looking at 48, I can pull out a 2 and a 24. Now 2 is prime, but 24 is not. So I have to keep going with that 24. So I can pull out a 3 and an 8. That 3 is prime, but that 8 is not. So I can pull out a 2 and a 4. 2 is prime, but 4 is not. And a 2 and a 2. Now all of my numbers are prime. So my prime factorization of 48 would be 2 times 3 times 2 times 2 times 2. Now we're going to look at simplifying radicals using that prime factorization. So those prime factorizations we already broke down. It was 3 and 9, and then 3 and 3. So I've got 3 times 3 times 3. Now, to simplify the radical, I'm going to keep the index, that should have been an index of 2, the same. And the rule is that we're going to pull numbers out in groups based on the index. So I'm going to pull out numbers in groups of 2 for this. So here I have 2 3s, so I can pull those to the outside. And I'm just going to pull out 1 because that's one group of 2 3s. And that other 3 is going to have to stay inside. So the simplified way to write the square root of 27 is 3 times the square root of 3. Now let's look at the fourth root of 48. So 2 and 24, 3 and 8, 2 and 4, 2 and 2. So that's 2 times 3 times 2 times 2 times 2. I'm going to use my radical, keep the index the same. Now I have to pull numbers out in groups of 4. So I've got 1, 2, 3, 4 2s. So that 2 can come to the outside. But I only have 1 3, so that needs to stay on the inside. So the simplified version of that is 2 times the fourth root of 3. Now I want you to practice some on your own, and then we'll go over them together. Okay, so first we're going to look at the cube root of 56. So I'm going to start by doing that prime factorization of what's on the inside. So 56 is even, so I know it can be divided by 2. So that's 2 and 28. 2 and 14. 2 and 7. Now I have all prime factors. So my prime factorization is 2 times 2 times 2 times 7. Now I want to keep my index the same, and my index is 3. So I'm going to have to pull numbers out in groups of 3. Well, I have 3 2s right here, so that 2 is going to come to the outside. The 7 doesn't have any matches, so it's going to stay on the inside. So the simplified version of that is 2 times the cube root of 7. Now we're going to look at the square root of 28. Now remember that the index, if there is no index written on the radical, is always a 2. So we're going to be looking for groups of 2 in this one. So I'm going to pull out a 2 and a 14 and a 2 and a 7. So I'm going to have 2 times 2 times 7. I'm looking to pull numbers out in groups of 2. Well, I have 2 2s, so that can come to the outside, but only 1 7, so that has to stay on the inside. So the simplified version of this radical is 2 times the square root of 7. And just to show you, if I had pulled out a different factor, so the square root of 28, let's say I had pulled out 7 and 4, I still would have ended up with 7 times 2 times 2. I would have had 2 2s, so they can come to the outside, and 1 7 on the inside, so I would have gotten the same thing. So as long as you're pulling out prime factors and breaking everything down, it doesn't matter which prime factor you pull out, you'll end up with the same answer. Now, another method that we're going to look at is the square root factor. And what this means is that we're going to look at all the factors of the number on the inside of the radical, and we're going to be looking for the factor that's a square root. So the factors of 27 are 1 and 27 and 3 and 9. Well, 9 is a perfect square, and the index is 2, so I'm looking for square roots. So this would be the square root of 3 times the square root of 9. Well, I know that the square root of 9 is just 3. So it will be 3 times the square root of 3. Which is the same thing we got before. Now looking at the fourth root of 48, that's an index of 4. So we're going to be looking for perfect fourths. And those are something we're probably less familiar with, so let's list out some of the perfect fourths. So I know 1 times 1 times 1 times 1, so 1 to the 4th is just 1. 2 to the 4th is 16. 3 to the 4th is 81. 4 to the 4th is 256. And 5 to the 4th is 625. So we'll just leave those to the side to help us. So I'm going to be looking for factors of 48. So 1 and 48, 2 and 24, 3 and 16, 4 and 12. And 6 and 8. Okay, now I need to look for a factor that includes one of those perfect fourths. So 16 and 3 is the factor pair that includes a perfect fourth. So this is going to be the fourth root of 3 times the fourth root of 16. Well, the fourth root of 16 is just 2. But we don't know the fourth root of 3 because it's not a perfect number. So we can just leave it as is. So 2 times the 4th root of 3. Now, personally, I find the prime factorization way easier, but I just wanted to give you the opportunity to see a different way to do it. Now you can practice using the square root factor, and then we will go over them. So looking at the square root of 32, want to remember that that's an index of 2, so I'm looking for perfect squares. So my factors of 32 are 1 and 32, 2 and 16, 4 and 8. Now, I've got 2 factors that are perfect squares here, 4 and 16. And the thing here is that I always want to use the biggest one because I want the other factor to be prime. So if I look at 4, its factor pair is 8, and 8 is not prime. But if I look at 16, 2 is prime. So I'm going to use this pair right here because 16 is the largest square root factor. So this becomes the square root of 16 times the square root of 2. And the square root of 16 is just 4. And the square root of 2 is imperfect, so I'm going to leave it the way it is. So simplified, the square root of 32 would be 4 times the square root of 2. Now looking at the next example, the cube root of 54, I'm looking for perfect cubes. So let's list out some perfect cubes. So 1 times 1 times 1 is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. And we obviously don't need to go any bigger than that because we won't be looking for factors larger than 54. So when I list out my factors, I have 1 and 54. 2 and 27. 3 and 18, and 6 and 9. And again, I have to be looking for perfect cubes because that was my index. So the only number in here that I have that's a perfect cube let me erase that. The only number I have in here that's a perfect cube is that 27. So that's going to leave me with the cube root of 27 times the cube root of 2. The cube root of 27 is 3. The cube root of 2 is imperfect, so the simplified version of this will just be 3 times the cube root of 2. Now we're going to look at simplifying radicals that have variables involved. So the biggest thing here is that we're going to simplify numbers normally. For variables, we're going to divide the exponent by the index. The whole number becomes the exponent outside the radical. The remainder becomes the exponent inside the radical, and we're going to keep the variable the same. So I'm going to run through this example with you to show you really quick. So first, I'm going to do the prime factorization of 625. You could do the square root factor. I just prefer to do the prime factorization. So if I look at 625, I know that I can divide that by 5, which is prime, and that would be 125. I can divide 125 by 5, and that would be 25. And 25 is 5 and 5. So I'll put my new radical over here. I'm going to keep that index the same. So I know that I'm going to pull a 5 to the outside because that's a group of 4 5s, and I won't have anything left to put on the inside. Now c to the 23rd power. I'm going to keep the variable the same on the inside and on the outside. I'm going to divide the exponent by the index. So 23 divided by 4 is going to leave me with 5, remainder 3. That 5 becomes the outside exponent, and the 3 becomes the inside exponent. So it's c to the 5th on the outside, c to the 3rd on the inside. And I'm going to do the same thing with d to the 11th power. 11 over 4. So 11 divided by 4. 4 can go into 11 2 whole times, which would give me 8. So then there would be a remainder of 3. So I'm going to have a d on the outside, a d on the inside. My outside exponent is going to be 2. My inside exponent is going to be 3. So simplified, this would be 5 c to the 5th, d to the 2nd, times the 4th root of c to the 3rd times d to the 3rd. And I know that doesn't look super simplified, but you'll see when we go to do operations with radicals why we have to simplify these things. So again, just to look at those steps, simplify your numbers. Normally for variables, you're going to divide the inside exponent by the index. The whole number, which was 5 or 2, is the whole number in our division, becomes the outside exponent. The remainder, which was in this case 3 both times, becomes the inside exponent. So let's look at one more example before we do some practice. So let's look at the cube root of 216. So first thing I'm going to do is do the prime factorization of 216. So that's 2 and 108, 2 and 54, 2 and 27, 3 and 9, 3 and 3. So when I look at that, I have a group of 2 and a group of 3 based on the index. So I'm going to have a 2 on the outside and a 3 on the outside. And now I can look at my variables. So for the m, 3 over 3 is 1 remainder 0. So on the outside, I'm going to have m to the 1, and on the inside, I'll have m to the 0. And if I look at the n, 6 divided by 3 is 2 remainder 0. So I'll have an n to the 2nd, n to the 0. So 2 times 3 is 6. M to the 1st is just m, n to the 2nd. Now if I look at this particular radical, m to the 0 and n to the 0 are both just 1. So that would end up being the cube root of 1, which is just 1. So there's no need to multiply this by 1. So in this case, these were all perfect cubes. So it's just 6 times m times n squared would be the simplified answer. Now I want you to try these two examples on your own before we go over them. All right, let's go over. So here I have an index of 2. I always want to write that imaginary 2 to help myself out. So 32, I would have 2 and 16, 2 and 8, 2 and 4, 2 and 2. And I'm going to pull those out in groups of 2. So 2, 2, and 1 left over for the inside. So in my final answer, I'm going to have a 2 on the outside, a 2 on the outside, and a 2 on the inside. Now for x, 4 divided by 2 is just 2 remainder 0. So since that remainder is 0, I don't have to put 1 on the inside. So I can just put x squared on the outside. And for y, 9 divided by 2 is 4 remainder 1. So y to the 4th, y to the 1st. So 2 times 2 is 4 times x squared times y to the 4th times the square root of 2y. Now let's look at the last one. On this one, we don't have any actual numbers, so we're just going to follow the procedure for the variables. We're still going to keep our index the same. So for w, 4 divided by 4 is 1 remainder 0. So that w can just come to the outside and it would be to the first power. For v, 17 divided by 4 is 4 remainder 1. So it would be v to the 4th, and then I have a v to the 1st on the inside. So when I simplify this, it's w times v to the 4th times the 4th root of v.